servers in a typical customer data center is actually enabled or have the capability to run any artificial intelligence solution, which means that it's very difficult for customers and users to embed artificial intelligence in your application stacks, which could be 20 years old, 10 years old. And without that equipment, we will have more compute capacity in our phone than in the data center. So everything I say, it's my own opinion. It is not endorsed by IBM. I'm working for IBM and sharing the information I have gathered over the years, but this is not a presentation which is, let's say, a product roadmap or statement of direction or anything like that. It's just for your, let's say, indulgement and for your enjoyment. So it's not a sales presentation. Now, that being said, I will spend the next 45 minutes or so discussing about enterprise AI, the introduction, the history, and the inferencing part of it. So enterprise AI is basically the branch of artificial intelligence which tries to embed artificial intelligence in everyday applications that are used by corporations. I will discuss a recent customer success. I will mention about the software required and the hardware required in order to make it happen, and what has been the developments over the years to where we are today. So we are in a very, very exciting time where we are in a paradigm shift, and which it's very important that we, if you are interested in data centers, computers, and technology, have a view on these developments. So I will start with the introduction and the background, because otherwise it's difficult to appreciate and understand what I'm about to present. So basically IBM infrastructure. So I'm in the IBM server infrastructure team. So you may or may not know that we sell 3 different kinds of systems. We have the IBM mainframe system, we have the IBM power system, which runs Unix and other operating systems, and we also market and sell storage solutions. So we have 3 distinct brands that we sell within IBM. And the 2 server brands, the mainframe Z16 and the power system, all use IBM-made microprocessors. We do not sell or use any x86 Intel processor or ARM processor. We make our own processors, and we make 2 different sets of processors. We have the mainframe processor, CPU, that runs in the mainframe computers, and we have the IBM Power 10 CPU that runs in the IBM power systems. And around those 2 server lines, we have designed different set of solutions that has existed since the 1960s and the 1990s, respectively, to support many businesses and new applications today. Now, why I mention these 2 is that both of them have adopted AI in different ways. So I would like just to share the differences in methodology and basically how it can reflect for you. And also all the storage solutions that we sell in IBM, we also call them scalable AI platforms. So all brands that we have are basically aligned towards embedding artificial intelligence in your everyday computing needs in your data center. So we have 3 different brands. I will talk mainly about the IBM power systems, but also compare with the mainframe, which is the machine to the left in the picture. So where are we today, and why do we need servers, and what can we expect in the coming years? If you are a computer scientist, scholar, or are interested in computing history, you may know that in the past, basically manufacturing technology allowed the performance to basically double each generation of computers. So we had a period until the mid 2000s where actually the performance of every new system was so much faster than the old one. It didn't make sense to prepare in advance. If you needed more performance, you just waited and bought the next kind of machines. Then around 2005, when we couldn't get that performance boost every generation, we started to add more cores. Up until 2000, mid 2000, most processors, most CPUs that you had in your laptop, in your server, they were a single core on a single chip. So when we couldn't make that single core any faster around 2003, we started to add more cores. So this is shared with all the vendors in the industry. It's IBM, it is Intel, it's AMD, and it's all previous generation machines, which we don't know anymore, but we started to add more cores. So you have in your laptop today maybe 4 cores, 8 cores, and we have also now started to differentiate between high performance cores and high efficiency cores to squeeze out that extra level of performance. So up until 2010, adding more cores really boosted performance as well, because we didn't have enough cores. But when we get to a point where adding more cores will not really help because my application cannot make use of it, what do? So it is expected now basically that to double the current performance that we have on a CPU today, on a processor, we have to wait another 20 years, which of course we cannot really wait that long. And if we don't have more compute capacity, how can we embed artificial intelligence in our applications? So, I mean, the hardware has basically plateaued in a sense. So we have to work around it. And what can we do? So one area where we basically say, okay, we cannot use the general purpose machine anymore. We need really to look at how to optimize for specific applications. This domain of computer engineering, computer science, basically is called domain-specific architectures. So by introducing domain-specific architectures, we could, for specific applications or specific problems, still get more performance than what we can get of a general purpose CPU or processor. So basically, for artificial intelligence, we talk about three different kinds of domain-specific architectures to, let's say, enable deep learning training workloads or inference. So we started with the GPU, the graphical processor unit, which is a graphics card originally, which we can utilize for these algorithms. And this is also very popular in high performance computing to leverage GPUs in order to scale, because even if your laptop have 8 cores, which is a very high number, if you have an application that can run over 1,000 cores, a GPU can help. So a GPU can run, let's say, a fewer set of fewer instructions. However, they can do it in parallel. So if you have a job that can be spread over 6,000 GPU cores, wow, those 6,000 GPU cores will be much faster than the 8 cores in your laptop. Hence, by having this enormous, massively parallel system, we could, for some problems, speed up the performance. But this doesn't help if you have a transactional database when you want to insert your salary and use the ATM. It cannot really make use of a GPU core. It needs fast IO, a fast single thread performance of a general purpose processor. So this is specific for certain, let's say, mathematical functions. And of course, if you want to watch movies, it's great to have a GPU. But that's why it's very popular with deep learning frameworks, because it can be massively parallelized and utilize the power of the GPU. That's why for artificial intelligence, a phone probably has much more AI capability than a server in the server room, because every phone has a GPU and it has a lot of parallel compute power that can be leveraged by frameworks. Now, the next level was that, okay, forget about training, because training, we train and we don't know, but it's expensive to have a GPU, the best GPU in the world, and we cannot really put a Volta 100 or the newest GPU in every machine in the server room, because we have 1,000 servers, and maybe we don't need to have it running all the time. So can we make specific hardware for inferencing? Because for a deep learning model, you train it on a data set and then you deploy it. So we want to make sure, okay, can we optimize the deployment? Like if you're a software vendor, you write an application, you compile it, you distribute it to your customer. Not every customer needs to recompile the application perhaps, or need to do it everywhere. So the scaling really happens actually on the inference. It's the inferencing that needs to happen everywhere to democratize AI. So it's the inferencing part, and Google started this trend with the TPU, which was originally a plug-in card specific for inferencing machine deep learning models. So it was the first step, the original TPU. Then TPUs got integrated in other circuits. And of course, if you have a lot of money, if you want to create a dedicated hardware device to do inferencing, be my guest. It's very popular, but it's very expensive, and if you need to change anything, you need to start from scratch. And this is unusual, but this is rarely, let's say, the most popular way of doing things. So instead, many people opted to look at FPGAs, field programmable gate arrays, which you can basically program with your model from time to time, and then the inferencing can run on it without communication with the programming device. So that is a way to update your model, because I want to deploy a new model. I can put it directly on the FPGA and it can inference my code, and it doesn't have to bog down my CPU, which is not able to effectively do this. So basically we have these three accelerators, you can call them, for artificial intelligence. Now, if we go back a couple of years in the IBM technology stack, so this is for a video analytics solution. On the left, you have a client that gets the video feeds from cameras. It basically communicates over the network to a deep learning engine to inference the video stream and give alerts, provide feedback, and report back. So communication happens over the network. It happens between the CPU and the GPU over the PCI bus. And typically, if you look back 3 years, we had PCI Express Generation 3, 16X as the biggest bus, and it was a little bit slow and it wasn't really that fast in terms of latency. Now, NVIDIA on their GPUs, on their graphics cards, at that time and still today, use NVLink to communicate between GPU to GPU. So what IBM did, went back to NVIDIA and said, hey, you know what, let's put NVLink on our CPU directly, so that the GPU can talk to the CPU much faster. We don't have to go over the PCI bus, and this will help to lower the latency, to improve the training time, and also the inferencing latency of the system. So this was really popular, and if you look at today, the world's number 4th and 5th high-performance computer in the world, it uses this Power9 technology with NVLink, talking to NVIDIA GPUs directly, bypassing the PCI bus. So this is a specific feature that we enabled in order to accelerate the training. So what on a typical x86 machine with a GPU looks like this. This is a runtime profile of a specific machine learning SnapML, which is an IBM machine learning model. It trains. Okay, so if you look at the time profile of this training process, I will compare it then with the NVLink version in the next slide. So you see it initialize, it trains, and then it has to wait to copy data from and to the GPU, initialize, trains, wait for the data, etc., etc. This is how it looks on the, let's say, a typical setup where the GPU is attached on a PCI Express bus. On the Power9 with the NVLink directly to the GPU, the training took longer than the copying of the data, so that could happen in parallel. Whereas on x86, it was the other way around. Copying the data took so long, we had to wait to train the data. So by improving the communication speed between the CPU and the GPU, this actually training process went 3.5 times faster on a Power9 machine with the same NVIDIA GPU as on the x86 machine. But by bypassing that bottleneck, which was the PCI bus, enabled us better times. Now, a typical solution, this is an example again from one of our previous solutions. To create a solution which uses artificial intelligence, you would need to have clients that get data, that send data over the network to a deep learning engine where the inference happens. You also had another set of data where you store the metadata, which would be used to retrain the model in a circle. So you have a complex system of at least 6 servers to run this software program to basically analyze the video feeds. So it's a complex, little bit cumbersome, let's say, architecture. Even though this is an elegant architecture, it is still a lot of moving back and forth. And the same machine that is used for training is used for inference here. So if your inference workload is very different from your training workload, why do I need to buy a very expensive top-of-the-line GPU that consumes 300 watts of electricity, which is not needed for the inference? Because inferencing is, let's say, the product, if in a video analytics solution, the inferencing would tell you, okay, there is a guy with a knife in the airport, raise the alarm. That's the inferencing part. That's the value part of the problem. The training can happen in the background, can happen separately, can happen in the cloud. Doesn't necessarily need to happen on the same infrastructure which is used to deploy the application. Whereas the inferencing really has to run where it is. So if the inferencing part is very different from the training part in terms of how it uses the architecture, maybe we can save money by not spending on a deep, expensive GPU on every system in the environment. Yes, it's basically discovered that the inferencing part requires much less accuracy in the data itself. So, for example, in the training part, you may need a 32-bit floating point, let's say, accuracy, whereas in inferencing you can have 8-bit or even 4-bit sometimes accuracy, and that is sufficient to generate a good accuracy. Now, if I have an 8-bit requirement, why do I need to run it on a 32-bit machine? And if I have a 32-bit machine, can I optimize it to be running the 8-bit queries in parallel? Okay, so yes and no. So for the V100 NVIDIA GPU, it could basically not, it has single-threaded, single precision performance of 15 teraflop. It cannot, let's say, optimize it, but with then the more much more cheaply T4 can basically quadruple that performance for lower bits. So basically, yes, for inferencing we need less accuracy. We can develop a specific T4 GPU instead of the V100, which is using only 1/3 of the electricity and can give actually for the inferencing 5 times more performance. Okay, so you can get 5 times better performance for the inferencing at a fraction of the cost of the training GPU. So that was the first step, to segregate, let's say, training and inference GPUs or equipment for that. However, it still leaves us the issue that if you want to run the inferencing, you still need to plug that device in your server, or yes, it is cheaper than the big V100, but you still need it. And if I look in a typical data center today, maybe out of 1,000 servers, maybe 10 of them will have a GPU. So I cannot train a machine learning model or deep learning model anywhere and deploy everywhere. I can only deploy on those 10 machines today, which is where the problem is we're trying to solve. So what is enterprise AI? So basically, it is trying to embed artificial intelligence where the transaction resides or the data resides. So if you have a transaction in a database, I want to run the AI in that database. I don't want to send it to some other system far away, waiting for the reply and get a response back. If I can run my AI model on the data where it resides, I can get much quicker results and I can get much higher throughput, because I don't need to send an API call to another machine across the data center and get a reply back. Again, the phone, it has everything built in. It is much better than a typical server in a data center. So how can we get that, let's say, data gravity and transactional gravity for the artificial intelligence problems that we need to solve? So this is a very, very key issue. Okay, and I will come up with 2 different responses, but that's one thing. And the second thing is a normal, so this is AI. What about mission critical workloads that run on our servers that we sell? So as I said, I'm from the IBM hardware team. We sell servers for mission critical workloads. Some of those workloads has been running for 30 years unchanged. And what do they require? Some of them require, let's say, real-time, near real-time response times. So for example, if you go to the ATM and you type your numbers, you want to get the money quickly. You don't want to wait 2 minutes and it times out and then you're stuck. If you need to implement an artificial model to basically do fraud detection on your ATM withdrawal, it has to act really fast. I mean, it really needs to act immediately. You cannot wait, because then again, the opportunity is lost. So that is one set of applications. Then we have basically other in the middle kind of applications. And then we have analytics, basically reports. Overnight, I want to analyze this usage patterns, this video data, batch kind of things, which is not really time sensitive or latency sensitive, but it's throughput sensitive. So can we basically solve both of these, or these three different use cases? How do we solve them? So the key is that we need to inference where the data resides. The training can happen in the cloud, anywhere you like, of that machine learning model, but we need to inject it where the data resides, where the transaction happens. And how can we do that? So as I said in the past, what we did is we put a GPU on that server. However, if you have a big virtualized server that runs hundreds of different workloads, we cannot have hundreds of GPUs in a single system, and sharing and caring, it's not going to be very easy. So how can we inference everywhere? Ta-da! The latest Power 10 processors and the latest Z16 mainframe processors have both basically put inferencing capability on the chip itself, on the processor itself. So by having it on each chip or each processor means that everywhere I run my application, I have the capability to basically score a classification engine. I can do my artificial intelligence inferencing where my data resides and where my application is running directly on the CPU itself. So it is not putting a full-fledged GPU on each CPU core or each processor. However, for the Power 10, which is the latest IBM Power processor that fuels the IBM Power Systems line, basically we already had vector mathematical engines, and by just adding an additional MMA matrix math accelerator engines to those, we could basically get a 6-time inferencing improvement by using those embedded scalar processor cores that's already in our architecture. So in Power 10, which is the latest IBM Power processor, the MMA accelerator is implemented on each processor core in the system. So in our system can have anywhere between 1 and 16 of these processors, and each processor can have up to 15 cores each. So we can have 240 cores of Power 10 processors in a single system, each of them having a matrix math accelerator capable of inferencing many typical deep learning models, basically. Where your data resides, where your application is running. We don't have to send the request somewhere else and wait for the response. We can basically inference that directly on the chip, on the CPU, in the core itself. So this is one way of doing it if you can. So let's put a AI accelerator in every processor core. So this processor supports virtualization, which means that many different applications or workloads can access the same core and at the same time, basically, which is okay. They can all use and utilize that accelerator feature, which is embedded in that processor core. Fantastic. So this scales really well. And in the results that we have seen is that it is about 50% faster to use it in this way compared to adding NVIDIA T4 GPUs for inferencing in some typical tests that we've done. So this can really inference well, better than a T4 NVIDIA GPU. And we don't have to send it away and wait for the response. So this is one way of doing it for one set of our servers, the Power System servers. We're adding this accelerator to the processor core itself. But just for fun, we also have the mainframe processor. The mainframe processor is a different CPU, and it works in a different way. It also has multiple cores. Each of these chips have 8 cores, where they, instead of putting AI inferencing capability in every core, they basically on every chip put an AI accelerator as a separate device. So the advantage here being that we don't need to change each individual core. We can just put an AI accelerator externally, and basically it can do the inferencing for all the cores in the system. Now, in order to do that, compared to doing the previous, it's a matter of let's say what you have and what you want to achieve. The good thing is that this scales with the number of chips up to 32. So basically, if you add more chips, you're adding more accelerators in the machine, of course, scaling that inferencing performance. And this has about 6 teraflops capacity, very comparable to an NVIDIA T4, which has in double precision around 4 teraflops. So it's very, very similar again, either putting it on each core or putting it on each chip separately. So these two, let's say, methodologies have been adopted by the latest IBM CPUs, which now have AI accelerators on top. They're not meant for training workloads. It is for inferencing, because they're not powerful enough to really train workloads. But the good part is that you can train your workload basically anywhere in the cloud, on your laptop, and basically deploy it where the data resides. So this is very exciting, and this is the next step. We're no longer adding GPUs to get AI inferencing capability. We're adding the AI accelerator on the chip itself, on the processor itself, in order for all the workloads that runs on the CPU to have access to that framework, which is lovely and wonderful. So as a eye-opener, so okay, what can we do with this technology? I'm going to talk about a customer example that happened in another Asian country for a hospital solution. So in pathology means that you take tissue samples of patients. Perhaps you have some kind of sunburn or mole, and you want to analyze it. So in the previous generation of this application or this system, basically the doctor would have to fill a form. He had to take the sample. He had to basically prepare the tissue on the slide. He had to send it to the laboratory. The doctor had to, let's say, review it. And if the doctor wasn't sure, he had to refer to another doctor for consulting and maybe refer it back in order to give a response back on what is wrong with my skin. Okay, it can take 2 to 4 weeks in order to basically do this chain one by one. So there are multiple areas here where it is, let's say, a little bit cumbersome. In this case, the language used in this country is made out of symbols. So it's very cumbersome for the doctor to type it on a keyboard. So it's much easier for him, for example, if you could basically talk and read out what he wanted to do, the form. So one area which could really improve the speed of this process, which maybe in some other countries may not be relevant, but here it was really that, can the form taking, basically, can I read out, instead of typing down my notes, can I read them out and the system can basically translate them to text for me? That would really save time for the doctor. And then instead of sending the slide to a guy with a microscope, let's scan the sample, okay, and use artificial intelligence to classify the image. And by doing that, he can directly send it to the right pathologist, because you may have 4 or 5 different pathologists with different speciality. If the artificial intelligence model can basically send it directly to the person most likely to be qualified to look at it, then the result will come back much faster. In this case, instead of 2 to 4 weeks, the result can come back in a few days. So why am I talking about this particular example? This is basically a system. It could even be a digitalized system that can really be benefiting from artificial intelligence. And I'm talking about enterprise artificial intelligence. I'm not talking about self-driving cars. I'm not talking about other stuff. I'm talking about traditional IT applications that could be enhanced, sped up by infusing artificial intelligence. And if we have the option of basically being able to run the inferencing everywhere, we don't need to have specialized machines in order to do that. And when we build our solution, all the machines can basically run this artificial intelligence inferencing as we go. So this is a picture of the hardware, and it's built on IBM Power technology, Power servers, and IBM flash storage. And we can see here that that the application interface is written in Windows, and the main database is to store this application, and the data is riding on the IBM Power machines running MySQL database. The post-processing and the AI inferencing for the tissue samples are done on the Power 10 machine, and also the image text to speech to text recognition. So they're stored on a common storage device with an IBM parallel file system, which is IBM Spectrum Scale, which means that the post-processing, the AI inference machine, he can see all the data as files wherever they reside. So he can see the data over the storage area network, which is shared with the other machines inputting the data. So we don't have to copy the data, we don't have to send it anywhere. He can basically run the inferencing as the data is loaded from the digital slide scanner. Okay. So the inferencing can happen on the data as it resides on the storage because of the unique capabilities of a shared file system, which is called Spectrum Scale. So again, the training in this case is happening on a PC with the NVIDIA A100 GPUs somewhere else. It could be in the cloud, it could be in your data center, wherever you have that capability. However, the patient solution, the production environment, the inferencing here is the value part. Inferencing decides which doctor will see the tissue sample and handle that. That can run on a mission critical Power 10 machine. And it's not relying on the NVIDIA GPUs on some machine far away. It is running on the CPU itself. The inferencing is happening on the CPU itself, removing any bottleneck of sending data back and forth. So this is the trend. This is the nirvana that we want to achieve. We don't want to have 1,000 machines in our data centers with GPUs in them. We would like to have 1,000 machines in the data center, each capable of running artificial intelligence on the get-go, in your hand. Because you're much more likely to use something in your hand than buying something else, something special for that particular job. Because you may have a different problem tomorrow, and you don't want to waste that money on something you may not need in the future. So I have here a calculator. I mean, why should you buy a calculator today? Everything is there in your computer, in your phone. However, 25 years ago, people still had calculators because there was the easiest way to access that intelligence or that capability. Now, today, nobody uses a calculator. And in the future, potentially nobody will buy GPUs to inference artificial intelligence workloads. And in order to scale and adopt artificial intelligence beyond experimentation, beyond the edge case, it really needs to happen everywhere. Wherever you want to run, you should be able to run your artificial intelligence. Whew. So how do we achieve that? If you have been following deep learning or even machine learning for some time, you know that you have a specific set of applications that you would like to use, and every data scientist has his favorite thing, and for every problem there might be a favorite framework. So, and as time goes on, also the fashion changes and let's say, and everything like that. So by having something that can support any framework, basically an interchangeable format like ONNX means that you can develop your application in any framework you want. You deploy it, you train it, and then you translate it into the ONNX framework, which can then be deployed on your machine. So in that case, your machine doesn't need to have that framework handily, because as soon as he has the ONNX framework, he can basically score, or he can inference those models. He may not be able to train them, of course, without a framework. However, you decouple the complexity of keeping all these frameworks, all the versions up to date. Oh, I have Python 2.7. Now I need Python 3. Oh, it's not compatible. I have to redo everything. We can decouple that complexity and the dependency on specific device drivers like CUDA, software, etc. You keep that with your model. Today, you want to use NVIDIA GPUs with CUDA. That's great. You train your model, fantastic. You deploy them over ONNX in your production machine, regardless of what you did or used to train the model. So having this interoperability is key to having this working, let's say, seamlessly. This also, because software changes much faster than hardware. So in 5 years' time, you may still have the same server with the same ONNX library. However, your training environment will have changed. You have different networks that you want to run. You have different applications that potentially you want to use. and you don't want to care about that right now, you want to invest in your data center, it should be able to run everything. So this is a very, very, let's say, appealing way of, let's say, making sure that I can inference whatever I want, wherever I want. So this is one key way. Another way, on the Power 10 architecture, we have different options. Of course, you can still deploy the same, let's say, framework, the same application set you use for training. You can deploy it directly on the machine. And if you have PyTorch, if you have this, if you have that, you can keep that up to date. So you can train your model in PyTorch and you can deploy it in PyTorch. You don't really need to have a portability layer like ONNX if you keep it one-to-one. It can still be trained on x86 and deployed on IBM Power, deployed on IBM mainframe, but you then have to keep the software stack up and running, which is another way of doing it. Yes, so a few other use cases, I mean, to really democratize AI when it comes to business applications is, for example, in the latest DB2 version, DB2 is a database engine developed by IBM. You can actually input Python or Pickle jobs directly into the database itself as stored procedures. So basically, using SQL, if you're a database administrator or transaction, you know what I'm talking about. You can basically say score this column with this AI model directly within the database itself. So again, you train your model anywhere you want. You can import it not only on the machine itself. You can import basically the artificial intelligence code directly into the database as a stored procedure. So this is one way of doing it that we are now supporting for this particular workload. Another way, I mean, on the IBM Power Platform, you can run many different operating systems. We have something called AIX, we have something called IBM I, and we can run Linux, you can run CoreOS. So basically here, if you run IBM I, it comes with its built-in database and applications on the same machine in another virtual machines. You can basically export your data using Kafka streams here, for example, score your, let's say, artificial model and basically put it back into the database. So by using virtual machines within the same server, you can basically shift data using APIs to a different VM that can run and score this particular artificial intelligence mode. So this is one way of doing it, let's say, which doesn't require you to import anything at all in the source. However, it is still running in the same server. And because all the cores can run this, it can run on any core in the machine. So this is running in the same server, however, in a different VM. And the same we can do with AIX operating system. For example, you run DB2 or Oracle database. You could basically have a VM running OpenShift here, for example, a container platform. You can deploy your TensorFlow or PyTorch things. And in this case, you can have clients connecting to that containerized OpenShift platform and basically fetching data in the backend from the transactional system running on AIX and basically acting as an intermediary between the client and the database, basically inferencing as we go along. So you can basically import it into the database itself. You can sidecar it on a different VM. You can basically set up a portal or a front end that does artificial intelligence on the same server as the database. And of course, the ONNX, that you train your model and then you infuse it with your application through this transparency layer. So thank you. This is really basically what I would like to, let's say, talk about in brief. So if you wonder, okay, can IBM help me? I need help with enterprise AI. Okay, so what is your strategy? Is it vision? Is it speech? Is it next level, next best action? Okay, we can engage you in different parts of the journey, and of course the result being we can run artificial intelligence inferencing on our mainframe on our IBM Power Platform, and we can help you enable your application here if you wish, if you have the requirement. So what have other customers, let's say, what is the feedback we have received? What have they told us? So we have really got very, very, let's say, favorable feedback. customers love the idea that they will be able to inference on the same core, on the same system where they run the core application. They don't need to send it off somewhere else and rely on some other unknown in order to infuse artificial intelligence in your business flow, because that particular server has an uptime requirement, performance requirement. If you send it off somewhere else, the complexity of the solution is exponentially growing. Hence, it is very, very appealing to most of the customers to run it exactly on the machine where the transaction is happening. So this is very, very favorable. And the conclusion, basically, what is the trend I see working in IBM, but as a general person, is that AI acceleration on the CPU is here to stay, and it is the way to democratize artificial intelligence, and it is a way to make sure that all the applications can add artificial intelligence without destroying the data center, without breaking the bank for most of our customers.